Hi. So consider you got this charger for your USB. You want to charge your phone, and you may know this takes about 5 volts to charge your phone, which is what's coming out of this USB, something around there. But of course, you want that in DC, and when you plug this into the wall, that's going into 120 volts AC. And I imagine there's quite a few steps that have to go into converting it from 120 volts AC to 5 volts DC. And the first thing you're going to want to do there is just drop that voltage down from 120 down to something closer to 5. And there's a couple other steps after that because you got to convert it to DC, which we'll discuss in another video. But for here, let's talk about just dropping that voltage down from 170 down to 5. And to do that, we need a transformer. So let's go into a little bit of the physics of how this transformer works, which is pretty cool. And then we'll go into kind of a demonstration, a simulation of how it works, and a little more the nuances of it. So say we got a AC voltage source here, and it's connected to this sort of a coil. All right, that's an AC source, but imagine for now that this current is coming this way. So if that current's coming this way, you could imagine we have a right-hand rule that tells us if our current's going in this direction, it's going to create this magnetic field that's around it. And if this magnetic field is coming in this way to the coil, and it's kind of going like this, and it's dropping down, you could imagine that as it's going around, that magnetic field is always pointed up in the middle of that coil. It's always up. So we can go ahead and, assuming the current's this way, we could say, well, it's going to cause this magnetic field upward here. And you could imagine that a magnetic field is kind of going to spread out like magnetic fields do. And you can take this magnetic field line and say it's coming out down here. All right, so imagine that as it's coming down over here, we've actually got another coil that's connected on this side. So maybe it looks something like this. And it's connected to some kind of load here. Let's just call this a resistor. Now that while this current going around this loop creates this magnetic field by itself is not going to create a current here. This is this magnetic field is created based on Ampere's law, but Faraday's law isn't quite symmetric, and it doesn't state that this magnetic field is going to cause a current. But let's go ahead and write out Faraday's law because it's still going to be important for us. Now, so what Faraday's law states is that this voltage that's going to be will be generated across this coil here, call that V2, is going to be equal to the change in flux over time, where this flux is what I'm representing here with these magnetic field lines, and the change over time meaning that if it's just stationary here, it's not going to do anything. It's actually got to be moving back and forth in order for it to create this voltage here. Also, I should note here that we've got a certain number of coils, and that's going to amplify this effect. So we'll call this N2 and say this is equal to 4, whereas this would be, on this side, we'll call this N1. In this case, it's also equal to 4, the way I've drawn it. And it turns out this N2 is important for this equation. It actually goes in here. So more coils means more voltage. And it turns out that this formula is actually going to apply to our left side as well. So we can say that V1 is equal to negative N1 times d phi dt. And now notice I use the same d phi dt here, but you could imagine, well, these aren't really the same because this is generating this magnetic field lines, and there's more lines here than there are over here. So this is going to be stronger because only a portion of it's getting over here. And you would be correct, but there's a way to remedy that, and that's by just putting an iron core here, a ferromagnetic material, and it can actually trap all these field lines in. So let's go ahead and show how that works. So this iron core will kind of keep those magnetic field lines in. But again, we needed this change in flux over time in order for this to work. So if the flux just constant there, it's not going to work. But thankfully, we drew an AC circuit here, right? So let's imagine that instead, if my current was flowing this other way here. All right, so now we're kind of going this way. And if you could imagine that if I'm going this way, and if I just kind of trace this back, what that current's doing, you can see that it's going to be pointed downward. So if when I reverse that current, it's going to actually reverse these magnetic field lines, and then it's going to be going back and forth. So I'm actually going to get this d phi dt as it oscillates back and forth with my changing AC voltage source here. So that's basically how the physics of transformers, sort of the intuition of how they work. And as you can imagine, that this current and these magnetic field lines aren't really visible, so there is more to this transformer than meets the eye. So let's go ahead and do a little bit of math here and figure out what this is actually going to do. So if we put this core on here, we're going to have, these are going to be the same. The magnetic flux through here is going to be the same through here, so we can sort of isolate this out. And let's say we just want to solve for this d phi dt right here. So we can say d phi dt is equal to negative v1 over n1. And then we can just go ahead and take this and plug it in for this d phi dt up here, and we can solve for this n2, v2. So now we've got v2 is simply equal to n2 over n1. And that's a pretty important one, so let's go ahead and box that in. And it kind of brings up this term here, this n2 over n1, that's an important ratio. And we're going to call this term a, but it's actually going to be n1 over n2. And let's go ahead and box that in, because again, this is very important. And let's go ahead and see how this works in a circuit. So what I'm going to do is bring up a circuit over here with a couple graphs for it. Okay, a little bit different way to represent this with some circuit elements. So we've got our AC signal source, and it's coming up, and it's going over our transformer here, and then on this side it's coming over to our resistive load. And you notice that there's no actually connecting circuits here. There's no lines connecting, but just like there wasn't over here, that this power is going to transfer sort of through the air. So this is our voltage source, and I'm going to show that down here in this graph, where this is going to be the voltage axis, and over here is going to be time. And on this side, we're going to have the voltage of our load, and that'll be represented down here in the same way. So let's see what happens when we turn this on. Okay, lots going on here. Let's first take a look at our voltage source here. So this is our voltage source. It's maxing at 170 volts, but you can see over here it's doubled. And that's because we have our A value is going to be at A equals 0.5. And according to this ratio, that shows that, that N2 is going to be bigger than that N1. So in this case, if we have A is less than 1, then we can call this a step up transformer, because you can see this voltage has stepped up. So this step up is with regards to the voltage. But while the voltage has stepped up, you see that comes at this cost, because you can see the current here is shown just by the way that these dots are moving, and it's going to be less on this side than it is on this side. So it's going to be actually reduced by half. And one analogy that is kind of close to this is with gears. So let's kind of take a look at some gears here. So this is your driving gear, and this is your driven gear, and you see there's like a bigger N number on this side because it's got more of these divots, and it's going to be actually have a higher torque. This the one on this side is going to have a higher torque, but you can see it's not going to be spinning as fast. The angular velocity is not going to be as fast. So it's kind of like here with the N2, you've got a higher voltage, but the current's not going as fast. Okay, so let's go ahead and stop this and see what happens if we change this to A equals 2 instead. All right, if we go ahead and run it, we see that we've got this voltage here that's at 170 like it was before, but over here our voltage has stepped down. So in this case we have A is greater than 1, it's 2, and this is called a step down. Also important. And you can notice that as the voltage stepped down, the current stepped up on this side. And again, we could take a look at this from like sort of a gear analogy and imagine that now we're going down from a higher end value to a lower end value, and it's going to have less torque, but it's going to be going have a higher angular velocity. So next let's consider what happens instead of this AC source, we put in a DC source. Okay, so here's my DC circuit. Everything's really the same. I changed a little bit of the resistance values, and then here's our DC source instead. So let's see what happens when we go ahead and start this. So our voltage source starts off high, but you can see the voltage over the load is slowly dropping. And if you kind of keep your eye on this current here, you'll see that current sort of slowing down. So moral of the story here is don't try using a transformer with DC. But last thing I'd like to mention is you may see this represented in a little bit simpler way, and that might be through a diagram like this, where we have our voltage source, just a line that's connecting it to this box. This box is our transformer X, and it may have a certain A, let's say it's 2 in this case, and then it may have a certain efficiency, say 99%, which is, you know, pretty typical. You can get above 99% efficiency in transformers, which is pretty surprising, but you can apparently get all those magnetic lines in pretty well. And say this is going to go connect to some kind of load. This would be a different way to represent a circuit like this, assuming, of course, that that was an AC up here instead of DC. So that's a little bit about transformers. But if you recall back to the initial question we had, it was, well, how do I get that 5 volts DC out of here? And we kind of talked about how you could step that down to, you know, from 170 something closer to 5. And the next step is converting that from AC to DC, and that'll be in another video. So until then, take care.